In the stillness of a deep night, when the sky drapes a soft blanket of darkness over everything, perhaps you're lying quietly in your familiar bed, letting your mind float somewhere among imaginary stars. As the glow outside the window gently fades and your breath falls into a slower rhythm, the ceiling above you begins to feel like it's opening into a wider sky. Those tiny points of light you picture become ancient lanterns of the universe, stars that burned billions of years before humans ever existed to witness them. In that peaceful moment, a thought rises softly, like a faint ripple gliding across the surface of a still lake. What if, before we fall asleep tonight, we drift together into a black hole? The idea, bold as it sounds, carries a strange calmness with it, almost as if the world around you is quietly expanding, deepening, softening with the darkness. Not a frantic plunge through cold cosmic emptiness, but an adventure woven from imagination and science. A journey that lets you ease slowly into the arms of one of the universe's most silent mysteries. A black hole. Its name feels like the image of perfect darkness, yet behind it lies a forest of questions, pages of physics both written and unwritten, and dreams pursued by generations of scientists. Tonight, we'll try stepping into that darkness, not with starships or special equipment, but with the pure curiosity that has traveled with humanity since the first night someone looked up at the sky. To begin, let your mind drift as gently as the stars spinning through infinite space. Then a quiet question appears, like a doorway opening to a new world. What lies inside a black hole? The universe, home to hundreds of billions of galaxies, trillions of stars, and stretches of space curved in ways no human eye can truly see, has kept this question hidden since the beginning of time. Each black hole is a secret wrapped in gravity, a place where even light cannot carry information back out. So every imagined journey toward one always carries that blend of awe and serenity, like standing before the grand entrance of a cosmic library. You know that inside lie all the unread truths, but the door only opens when you're ready. And tonight, you won't walk in alone. We'll have a companion with us, an imagined astronaut, not with a fixed face, not needing a name, existing simply as a symbol of the gentle courage humanity brings to its greatest explorations. This companion will travel with us to the edge of space-time, through shadows, observing things science is still trying to decode. Not a cinematic hero braving danger, but a quiet soul drifting among the curves of the universe, representing anyone who has ever lain awake, stared into the night, and wondered, is something waiting behind that darkness? Imagine you and this silent companion standing beneath a wide open sky, where distant stars stitch together a shimmering tapestry. From here, everything seems to pull back, soften, slow. The Milky Way stretches into a pale ribbon, like a still river flowing through an endless night. At the exact point where all those distant lights meet your gaze, our story begins. A story that doesn't need urgency or dramatic turns, only your presence, your willingness to understand the universe while still holding on to the calmness of each breath. In this quiet moment, the black hole becomes something more than a textbook object. It becomes a doorway, one of the fundamental gateways into the deepest questions humanity has ever asked. What is space really made of? What does time truly mean? Where does information go? And could anything exist beyond the limits science has drawn so far? All of these ideas will come in their time, but for now, we only need to sit gently beside the question. What is truly inside a black hole? Tonight's journey isn't meant to deliver a final answer. The universe hasn't given one yet, and perhaps it never will. Not in the way we want. But this journey is a place where the lightest thoughts drift like stardust, where complex science turns into calm, flowing streams so you can learn, relax, and let imagination carry you just a bit further. All you need to do is let yourself drift with it, accepting that not everything requires a clear conclusion, and that the most mysterious things are often the most beautiful. When you picture a black hole, you might feel both its silence and its enormity. It is a place of absolute darkness, yet also a spark for the brightest imagination. And tonight, as the story gently unfolds, you'll drift slowly toward that world. The world where darkness isn't a threat, but a tender invitation from the universe, whispering that countless wonders remain undiscovered. We'll go together. The journey begins here. While the question of black holes still lingers like a soft glimmer against the quiet night, the image of the astronaut companion grows a little clearer in your mind. Not to add drama, but to ease us into the next part of the journey. If we've already agreed to fall into the universe's darkness in search of answers, then this journey needs a place to begin. And that beginning comes from the most familiar place of all, Earth. Let that idea open like the second doorway in our story. No surprises, no urgency, just the natural continuation of a drifting thought. From the dim room, your imagination expands toward the sky. And from that sky, Earth appears as a gentle blue sphere turning slowly in space. The place where you lie, the place where every memory, every laugh, every rhythm of life unfolds, shrinks into a soft point of light in the vast universe. And from that glowing point, our imagined voyage begins. Let your mind sketch out the spacecraft, quietly floating in low orbit, resting above the swirling white clouds wrapped around Earth. Then picture it gently slipping away from orbit, distancing itself from the familiar world. There is no noise, no shaking, only the feeling of looking back and watching Earth grow smaller, bit by bit. The blue of the oceans, the brown of the continents, the threads of city lights at night, all merging into a small, delicate gem drifting through darkness. That planet has cradled life for billions of years, and even though the mysteries of the cosmos stretch infinitely outward, Earth remains the place our thoughts always return to. As the planet fades behind you, the space ahead opens like a shoreless ocean. Distant nebulae emerge like faint wisps, and the Milky Way arches across the sky like a silver river flowing endlessly through hundreds of billions of years. Looking into space feels like lying inside a vast room whose ceiling is hung with lanterns suspended light years away. Each lantern is a sun, each sun a solar system, and each system holds stories we've never heard. In this space, the sense of our smallness doesn't spark anxiety. It brings a strange peace. Not because we're insignificant, but because the vastness of the universe grants us permission to let go of every weight we carry and simply listen to its slow, gentle movements. Your breathing falls into a steady rhythm, light as if drifting in an invisible sea. The feeling is like slipping into a warm bath on a chilly evening, except what you're sinking into isn't water, but weightlessness. Imagine the astronaut floating inside the spacecraft, neither pulled down nor lifted up, supported only by perfect silence. The body feels almost absent, the mind freed from the familiar ties of gravity, and in that moment, every sense softens to its quietest setting, leaving only a dreamy awareness of the infinite space unfolding around you. From that calm, a dark point appears far away. Not a frightening shadow, but a deep and inviting one. A black hole, somewhere within the Milky Way, hidden among swirling ribbons of heated gas, waiting in its quiet way. No pursuit, no looming danger. Simply a destination to understand, a question waiting to be approached. And that thought slips gently into your stream of awareness. A soft voice saying, "Out there, in the depths of space, a black hole is waiting for us." The journey toward it doesn't happen with roaring engines or high-speed storms. In this sleep-bound imagination, the spacecraft drifts slowly, like a leaf gliding across a still lake. There's no need to rush. The black hole is unimaginably distant, so far that light itself would take thousands of years to reach it. But in the space of our story, that distance compresses into a soothing sense of slow travel, not shortening the path, but lengthening the calm that comes with entering the universe. When you peer out the imagined window, Earth is now just a faint blue dot among the cool white stars. No borders, no sound, only the peace of a moment that feels like lying in a hammock under a summer tree. This is one of the rare moments when the mind can slip free from the noise of the world, settling into the gentle motions of the Milky Way. The Milky Way now appears as a soft spiral where hundreds of billions of stars circle the galaxy's center like tiny lanterns in an ancient cosmic dance. From here, the galaxy looks like a painting made of light and shadow, and somewhere near the center, hidden among dense clouds of dust and gas, immense black holes reign like deep wells in space-time. We don't choose a destination yet. We simply allow the mind to grow comfortable with the truth that black holes aren't mindless devourers, but natural, majestic structures of the cosmos. In this slow drifting space, the astronaut companion is like a gentle compass guiding the journey, without moving, without giving instructions. Their presence is purely symbolic, a reminder that this exploration is shared by curious minds willing to drift along with science and imagination. The feeling of companionship makes the universe feel less vast, less lonely, like sitting beside someone on a quiet beach, watching the waves without needing to speak. And then, as everything settles, as the imagined breath becomes slow and deep, as Earth fades and the distant black hole grows clearer, the story opens into a new chapter. We are preparing to drift deeper into the darkness, to understand what light cannot tell us. But before stepping into that mystery, all we need to do is keep floating, keep watching, keep letting the mind rest in the vastness of the cosmos. The journey has begun this way, and from here, the black hole's darkness will slowly become the light of understanding. As the imagined spacecraft continues drifting through the quiet void, the distant black hole remains just a tiny, dark speck among countless starlit points. Everything around feels as light as mist, as slow as a nighttime current, letting the mind slip easily from the feeling of floating into a gentle curiosity. And just as the mind settles into that suspended calm, a familiar question slowly rises from deeper layers of thought. If this journey is heading toward a black hole, then first, what exactly is a black hole? The question doesn't demand an immediate answer. It simply rests there, like a faint glowing particle spinning quietly in space, waiting to be touched. Let your imagination open gradually, like a flower unfurling in the quiet of night. In the vast canvas of the universe, among the light of billions of stars, there exist pockets of absolute darkness, places where light cannot escape, and all information is held in perfect silence. Those dark pockets are black holes, some of the strangest creations nature has ever formed. Not holes in the physical sense, but regions of space where gravity is so intense that even light, the fastest traveler in the cosmos, cannot carry its stories outward. If we borrow the gentlest language of a peaceful night, we can picture a black hole as a bottomless well tugging at the fabric of space-time. That fabric, usually smooth and soft, is pulled downward so deeply that anything passing near the well's rim slides inward and cannot turn back. There's no need to imagine violent power. Just picture that fabric sinking into a deep, unending dip where every possible path leads inward. And when we speak of black holes, there is a delicate concept we need to remember: the event horizon. It is the boundary surrounding a black hole, the invisible line beyond which no signal can return. Imagine it as the rim of that bottomless well. Outside the rim, light can still curve around, wander away, or tell the universe what it has seen. But once it crosses that boundary, every escape route disappears, and every moment afterward must move deeper into the darkness. The event horizon isn't a wall or a physical membrane. It's invisible, a boundary defined by mathematics and physics. Yet in imagination, it can be seen as the thin threshold between the world we can observe and a world no longer belonging to light. That invisibility is part of what makes black holes so mysterious. No warnings, no floating signposts in space, no sound or telltale glow. Only a shift in fate for whatever crosses it, from freedom to no return. To understand black holes in the most sleep-friendly way, there's no need to dive into equations or complex symbols. No physics homework here, no long proofs, we simply imagine. Imagine with the softness of dropping a dry leaf onto still water. In this nighttime adventure, imagining is more important than analyzing. Sensing the idea is more important than breaking it into formulas. The universe gives us permission to dream inside science, letting rigid concepts soften and drift with the rhythm of sleep. Picture the astronaut companion observing the black hole from afar, millions of kilometers away. In that imagined gaze, the black hole isn't frightening. It doesn't rush toward everything like in dramatic movies. Instead, it is quiet and still, like a dark lake surrounded by light that bends gently around it. Near the black hole, starlight is warped, as though space-time were liquid glass. A faint ring of light appears, not touching the black hole, but circling it like a ghostly halo. That light ring doesn't come from the black hole itself. It's made of starlight bent to the extreme, a subtle sign that space-time is stretched to its limit before disappearing completely beyond the event horizon. The closer we move in imagination, the more deeply the fabric of space-time curves downward. Nothing like any pull on Earth. Not a harsh force, but a slope so smooth that anything crossing it slides inward without meaning to. The deeper it slides, the harder it becomes for light to escape, and the stranger time behaves. But all of this is just imagery, a soft illustration painted from a mix of science and imagination. In this moment, relaxation can spread gently like small waves. The image of the black hole becomes a dark, blurry circle against a star-bright sky, foreign yet gentle. No alarm sounds, no warnings, only a heavy, quiet darkness holding secrets the universe has not fully shared with us. And while the imagined spacecraft seems to hover before that darkness, the story doesn't pressure us to understand everything at once. A black hole is wide, deep, layered. But to begin exploring it, we only need this quiet picture. A region of space sinking like a bottomless well, surrounded by an invisible boundary through which light cannot return. From here, The journey will unfold into deeper layers of science and imagination. But this first picture is the soft foundation that allows everything else to appear gently, like little points of light drifting in an endless night. As the image of that bottomless well of space-time drifts gently through your thoughts, the journey quietly opens into another direction, subtle but deeper. If a black hole can be imagined so effortlessly, then the next question naturally arises. How do we know these bottomless wells actually exist? What convinces us that a perfect darkness in the universe is real, when even light cannot escape it? From the gentle picture of the black hole, this idea leads us back to distant days in the history of human thought, when scientists, too, stood in their own kind of darkness, feeling their way step by step, much like we are doing now. The story begins in the 18th century, when the idea of a dark star was proposed. At that time, physics had no concept of curved space-time, nor the understanding of light speed as an ultimate limit. And yet, someone wondered whether a star large and heavy enough might pull so strongly that light could not escape its surface. The idea sounded simple, almost primitive, like an early, hazy guess made at the dawn of scientific thinking. But it became the first dot on the map of black holes. Though no one could verify it, what mattered was that someone had dared to ask the question. That question was like a seed falling into soil, waiting quietly for the right time to grow. Time passed, and nearly 2 centuries later, a great door opened when Einstein introduced the theory of general relativity. Instead of treating gravity as an invisible pulling force, Einstein described it as the curvature of space-time. Think of the fabric we imagined earlier when speaking of a black hole. It was Einstein who showed that this fabric could bend under the influence of matter and energy. The heavier an object is, the deeper the curve. A massive star, or any extremely dense form of matter, can make space-time dip as though tugged down by a weight. From this description, the idea of the bottomless well became clearer, more tangible, no longer a lonely speculation. But even then, general relativity was still a beautiful but abstract framework. Einstein didn't immediately think of black holes in the modern sense. He simply opened a new way of seeing the universe. The deeper steps would come from others. One of those people was Karl Schwarzschild, a German physicist working under the harsh conditions of the First World War. In the mud and chaos of the battlefield, he found the first exact solution to Einstein's field equations. That solution described a strange kind of space, where every possible path leads to a single point. Though Schwarzschild did not live long enough to witness the impact of his discovery, his equation became the foundation of the black hole concept we use today. Yet the journey from equations to a shared human intuition was still long. Decades later, when the math existed, but the imagery had not yet taken root, another physicist stepped into the story, John Wheeler. He was the one who gave the object its name, black hole. Simple and powerful, the phrase transformed how people understood this mysterious structure. Instead of technical terms and cumbersome descriptions, the new name offered a direct, evocative image, like a doorway into the deepest darkness of the universe. The name spread like a gentle wave, accepted by scientists, then embraced widely. Thanks to it, black holes left the boundaries of academic papers and entered the world's imagination. This historical story isn't meant to teach formulas or walk through complicated calculations. It's a slow, flowing stream that carries us past the milestones marking how humanity came to believe in regions of absolute darkness. From a simple idea, to a beautiful theory, to an elegant solution, and finally to a name that allowed the concept to breathe in the collective mind. The journey is like following faint footprints in sand, each one adding a fragment to the larger picture. What makes this story gentle is realizing that scientists, no matter how brilliant, once stood in the darkness of the unknown just as we do. They had no modern telescopes, no computer simulations, no data on gravitational waves or radiation swirling around black holes. They had only intuition, curiosity, and the belief that the universe holds secrets waiting to be uncovered. Each idea they proposed was a small candle lit in the dark, and together those candles slowly illuminated the path we now walk. When we look back on that journey in the slow, drifting rhythm of the night, a black hole becomes more than an abstract scientific notion. It becomes a centuries-long story, each generation leaving a layer of thought, a step forward, a dream. From dream to formula, from speculation to description, from obscure papers to the breathtaking images modern humanity can observe. All these pieces merge into a gentle flow of human knowledge. And within that flow, we drift forward toward the mysterious darkness, feeling as though we are continuing the long chain of thought begun by countless minds before us. As the story of the history of black hole ideas comes to a close, from the faint sketches of an invisible star in the 18th century, to Einstein's bending equations of space-time, from Schwarzschild's solution to the moment John Wheeler gave this object a short yet weighty name, the journey gently carries the mind toward another question. Not only how humans once imagined black holes, but how black holes themselves are truly born. If the ideas of scientists reveal the evolution of human thought, then the birth of a black hole reveals the evolution and the ending of the universe's massive stars. In the softest way, you could say that every black hole is the remnant of a star that once blazed brilliantly. No black hole exists fully formed from the beginning, except in distant hypotheses about primordial black holes. Most of them start as enormous spheres of gas, radiant, burning, living for millions or even billions of years. Those giant stars are like natural nuclear furnaces, forever fusing hydrogen into helium and then into heavier elements, releasing light and heat into the vastness around them. But like anything in the universe, the star's fuel is finite. Eventually, these nuclear furnaces reach the end of their run. When a star massive enough, far larger than our sun, exhausts its fuel, the balance between the outward push and the inward pull collapses. Its core loses the thermal pressure it once had to resist gravity, and it begins to fall inward on itself. This collapse is not slow or graceful. It happens with a violence beyond imagination, matter rushing toward the center with staggering acceleration. And then, in that crushing instant, when the core is squeezed into something unimaginably dense, a supernova erupts. A supernova is one of the brightest events in the entire universe. In the final instant of its life, a star can shine brighter than a whole galaxy. The light from that explosion travels across millions of light years, like the star's last farewell to the cosmos. It blasts away its outer layers into vast clouds of gas, brilliant remnants that humans later observe with awe. And in the midst of that glowing chaos, the star's core continues to collapse. If the mass is large enough, gravity becomes so overpowering that nothing can stop the fall. Matter is crushed into a point so small that no known force can resist it. And from that point, a black hole is born. You could say a black hole is the final inheritance of a star that lived its life to completion. And in the quiet darkness of that black hole, you can still feel the echo of its formation. When a star dies, it leaves behind a secret, a black hole, a region where space flows inward like water into a well, where time itself stretches toward infinity. On his journey toward a black hole, the astronaut in our story might drift past supernova remnants, soft tapestries of color scattered across space. There are wisps of blue, deep red, and muted violet swirling around each other like brushstrokes painted by the universe itself. These clouds are where heavy elements were cast out by the explosion: carbon, oxygen, iron, the very elements that later form planets, oceans, forests, and even life. As he glides through them, it's as if the astronaut is passing through the history of the universe's matter, the same history that ultimately leads to the creation of black holes. Although most black holes come from the death of massive stars, nature has other paths. Some theories whisper about primordial black holes, ancient black holes born right after the Big Bang, when the universe was so dense that small pockets of high energy may have collapsed into black holes within the first thousandths of a second. If they exist, they would be tiny, almost impossible to detect, yet carrying properties very different from those created by dying stars. On the opposite end of the spectrum, the supermassive black holes at the centers of galaxies remain one of cosmology's deepest mysteries. Their masses reach millions to billions of suns. No one knows exactly how they were born. Perhaps they grew from smaller stellar black holes. Perhaps enormous clouds of gas collapsed directly into them. Or perhaps they formed extraordinarily early, before galaxies themselves took shape. These possibilities remain only sketches, lying at the soft edge of human knowledge. But for the astronaut in our story, the black hole he is approaching is a supermassive one. Because such black holes carry a curious gift. The tidal forces at the event horizon are not overwhelmingly strong. That means he has time. Time to observe, time to drift, time to sense the darkness before his body is pulled apart. This is what allows our story to unfold slowly, gently, in a rhythm soft enough for listeners to drift toward sleep. As the astronaut continues through the fading remains of ancient stellar explosions, the light is no longer as brilliant as in the moment of the supernova, but it still glows softly enough to create a delicate scenery, a thin cloud stretched across his path. It is a journey through the final pages of a star's life, leading toward the first page of a black hole. And when the last layers of stellar remnants drift behind him, the story gently shifts to what comes next, where the structure of the black hole begins to appear, like concentric circles guarding an ancient cosmic secret, as the tale of a star's radiant death still lingers in the mind, like the distant echo of a fading supernova. Our journey drifts quietly forward, toward the growing darkness left behind by its collapsing core. From a tiny remnant so dense that space-time itself must bend around it, the black hole begins to emerge as a complete entity, with its own structure, its own layers, as though it, too, possesses a kind of body. Gentle contours the universe has spent billions of years shaping. As our imagined astronaut moves closer, these layers of darkness slowly reveal themselves, like faint concentric rings separating from the endless night. If we see a black hole as one of the universe's silent beings, its first feature is the one we encounter at the boundary, the event horizon. This is the invisible line encircling the absolute darkness within. Not a wall, not a veil of smoke, just a boundary beyond which every return path disappears. Picture a circle that no ordinary eye can see, yet one of the most fundamental borders in the universe. Outside this circle, light can still escape. Inside, even light cannot whisper a final goodbye. The event horizon, is like the rim of a bottomless well, where the slope of space-time becomes too steep, too sheer for anything to climb back out. It is the surface that defines the very idea of a black hole, dividing the observable universe from the realm of total silence. No sound, no signal, no warning. It exists only through mathematics, yet in the imagination, it becomes the stillest circle in existence. Moving just a little closer to this edge, we meet another strange region, the photon sphere, the place where light is forced to orbit the black hole. It is not where light is swallowed, nor where it is free to escape. It is a fragile path where even the slightest deviation sends the photon spiraling inward or flying away. Imagine beams of light held gently in place, looping around the silent core as if tracing a delicate celestial pathway. That orbit is neither loud nor dazzling, yet it is among the most exquisite phenomena space-time can create. If the astronaut were to gaze toward it, the light from behind him would bend so dramatically that it would form surreal illusions. A star appearing where it should not be, a streak of light stretching out like a silver thread across the darkness. Beyond the photon sphere lies another structure, not part of the black hole itself, yet often associated with its glow, the accretion disk. As matter falls toward a black hole, it does not plunge straight down. It spirals, warming until it glows like ribbons of fire revolving around a silent heart. But in this gentler version of our story, the accretion disk need not appear as the violent inferno of science fiction films. You may imagine it instead as a soft ring of drifting gas, glowing in pale gold or cool blue, depending on your imagination. Though in reality, the disk can reach temperatures of millions of degrees, in this sleepy journey it becomes only a slow, steady halo, circling the black hole like a luminous necklace against the deep night. And sometimes, around rapidly spinning black holes, two slender jets of matter shoot out from the poles, stretching for light years. In the real universe, these jets are streams of ultra-powerful plasma. But here, in this quiet narrative, we pass them merely as distant streaks of light, silent, unmoving, like twin pillars shining in the cosmic dark. They do not belong to violence, but to a strange balance between matter and space-time. If a black hole had a profile, then alongside these imagined structures, it would also carry a set of defining parameters. Its mass, its Schwarzschild radius, its spin, and in some theoretical cases, its electric charge. Mass determines the depth of the gravitational well. The Schwarzschild radius marks the size of the event horizon. Spin tells us whether the black hole rotates, and how fiercely. These details are like tiny notes in the record of an absolute cosmic object. We need not analyze them deeply, only know that the universe quietly sets these standards to describe its perfect shadows. As the astronaut drifts closer, the light around him begins to bend. The distant stars no longer stay where they should be. They stretch into thin arcs, then blend into a ring of luminosity curved by an unseen artist. It is not an illusion. It is space-time itself bending more intensely. Light, the swiftest thing we know, is forced to follow these curves, leaving behind a scene almost impossible to describe. And in the universe's vast silence, this spectacle feels like a slow, graceful dance, where everything moves along soft, sweeping lines. All these layers, the event horizon, the photon sphere, the accretion disk, and the distant jets, come together to form the body of a black hole. Not a living body, but a unified, enduring, profoundly mysterious structure. Viewed from afar, it is nothing but darkness. Yet as one approaches, The layers unfold like concentric circles, guiding the observer inward, gently, without force. And now, as the astronaut drifts into the region where light itself begins to warp, the story also moves closer to the black hole's most secret center. These outer layers are only the beginning. Much more awaits within the depths of curved space-time, and this journey, soft as a breath, will continue carrying us into those deeper realms, where time, light, and all familiar rules begin to shift in impossible ways. As the image of light bending around a black hole still drifts slowly through the mind, the journey opens a new branch, gentle, like a stream changing direction, without leaving a ripple behind. If a black hole can possess its own structure, with layers of darkness wrapped around an inescapable core, then the next question naturally arises. Are all black holes in the universe the same? Or do they too have relatives? Different sizes, different origins? From the silent space surrounding us, that idea unfolds like a door opening into an entire family of cosmic shadows, each kind carrying its own story of formation. Let us begin with the most familiar black holes, born at the end of a massive star's life, when its core collapses and a supernova erupts. These are called stellar mass black holes. Their masses range from a few times the sun's to several tens or even hundreds of suns. The space around them curves into a deep well, though not an overly wide one. If a spacecraft drifts too close to such darkness, the uneven pull from both sides becomes so intense that everything stretches into long, thin strands. This is where tidal forces reign, making these black holes unsafe for any journey that seeks quiet. They exist throughout the galaxies like scattered dark points, recording in silence the deaths of ancient stars. Moving deeper into the dense, glowing regions of the universe, toward the centers of galaxies, we find another group, supermassive black holes. Their masses reach millions or billions of suns, enough to warp space-time into an immense, plunging valley. What's remarkable is that despite their monstrous mass, the edges of their event horizons are surprisingly gentle. The uneven pull there is far weaker than around smaller black holes. This makes them the safest destination for our drifting astronaut. If one had to choose a friendly darkness to fall into, this would be the brightest candidate. Between these two groups, scientists have long wondered about the existence of a middle branch, intermediate mass black holes, heavier than stellar black holes, but far lighter than supermassive ones. For years, their existence was only a suspicion, a missing piece in the family portrait of cosmic shadows. But subtle observations have revealed indirect hints, making their existence increasingly plausible. Even so, compared to their more prominent relatives, they remain rarely seen, like distant family members who appear only in a few blurry photographs. And finally, in the deepest corner of imagination, there is a type of black hole no one has ever observed: primordial black holes. These arise from the idea that shortly after the universe's birth, when everything was dense, hot, and wildly chaotic, tiny fluctuations in matter, density might have collapsed into incredibly small black holes. They could be as light as a mountain or as heavy as a compressed grain of dust. Though unobserved, the idea sits like a faint echo, both mysterious and bold, reminding us that the universe still holds vast territories our knowledge has barely touched. If we see these four types as a family, each one is a different generation of darkness, carrying its own origin story and way of existing. But in this sleepy journey, where gentleness matters more than intensity, we choose the safest of them all, the supermassive black hole. large enough to curve space-time into a colossal basin, yet gentle at the edges, giving our astronaut time to contemplate before going deeper. No sudden tug, no tidal tearing, only a slow, quiet drift into the waiting dark. In imagination, the astronaut gazes ahead, toward a supermassive black hole surrounded by the faint glow of a distant accretion disk. It is not a lonely dot of darkness, but the center of a softly turning halo of light. At a safe distance, space-time bends around it as gradually as a ribbon's graceful curve. Approaching it does not feel like being dragged downward, but like being gently invited by a region of space that moves in silence. The supermassive black hole becomes our chosen destination, not because it is less mysterious, but because it allows the story to unfold completely. A small black hole would pull everything too fast, too fiercely, turning the journey into something rushed and violent. But near a supermassive black hole, time appears to stretch, leaving room for imagination to drift along curved rays of light, leaving space for questions to find gentle anchors. Here, the universe does not flare or vanish. It simply settles, calm as a night lake. And so, among this vast family of black holes, the astronaut has found the place he will head toward. A giant shadow deep within the Milky Way, where light circles and space-time bends like an elegant arc. From this point forward, the journey will shift from observing the outside to approaching the boundary of the mystery itself. And as space begins to slope downward like an invisible incline, the story will follow that slope, slowly, softly, into the deeper darkness where the universe keeps its most silent secrets. With the destination now chosen, and the image of the supermassive black hole rising like a dark ring trimmed with distant light, the journey begins to move into a region where the universe's familiar rules soften and become stranger than ever. From the family of black holes with their varied sizes and origins, the thought drifts naturally toward a new question. Quiet as a stream that changes course without disturbing the surface. What happens to time as we approach the edge of a black hole? If space-time curves downward into a deep well, does time itself bend as well? The question floats open like a suspended doorway, leading us into a realm of wondrous ideas, where imagined clocks no longer tick as they once did. In the world Einstein described, gravity does more than pull on matter. It slows the flow of time. The closer one is to a region of strongly curved space-time, the more time stretches, like silk being drawn gently apart. As the astronaut approaches the supermassive black hole, his own time moves as usual. Moments follow one another steadily, like turning the pages of a quiet evening book. But to a distant observer, his journey unfolds with extraordinary slowness, as if nearly paused. A single second for him may stretch into minutes or hours for the one watching from afar. This is gravitational time dilation, one of the marvels that makes black holes the most enchanting doorway in modern physics. Imagine two clocks, one carried aboard the ship drifting toward the black hole, the other sitting far away, where space is flat and time flows evenly. At first, both clocks beat in unison, but as the ship nears the region of stronger curvature, the clock on board begins to slow. Not because of malfunction or error, but because the nature of time itself has changed. For the astronaut, everything feels normal. His heartbeat, his thoughts, the shimmering impressions of the bent light outside, all flow at the familiar pace. But to the distant observer, each movement appears as though it takes place in thick liquid, gently slowing bit by bit. From far away, the observer would even see the astronaut freeze at the edge of the event horizon, as if his time were locked in place at the border of darkness. But he is not frozen at all. He continues drifting downward into the well of space-time. It is simply that the light carrying news of his motion has been stretched toward infinity, turning every update into something slower, fainter, dimmer. Meanwhile, for the astronaut, it is not his own time that slows. It is the time of the universe outside. From the quiet interior of his imagined spacecraft, if he were to look outward, he might see the stars shifting position faster than before, the light of distant galaxies sliding in color as though the whole cosmos were speeding up. This is the gentle reversal of perspectives. His time flows steadily, while the time of the outer world races like a fast river. If we imagine further, a soft paradox appears like a thin curtain. While the astronaut falls into darkness, millions of years outside may pass. As he follows the curve of space-time, the world beyond will age, stars will fade, galaxies will reshape themselves, and human civilization may transform beyond recognition. Though this sounds like science fiction, it is a perfectly natural consequence of gravitational time dilation. A true story, but soft as a dream. Near the edge of the black hole, the line between time and space becomes less defined. The paths of light, the quiet rhythms of space-time, they blend into one elongated tapestry. The astronaut is nearing a place where the equations of physics begin to whisper in a different language, where the ideas of before and after lose their sharpness. Not in a frightening way, but in the same gentle manner you might lose the sense of where a wave begins or ends while floating beneath warm, calm water. In this stream of reflection, time is no longer felt as a rigid chain of links, but as a soft scarf the universe wraps around its events. When we pass through strong gravity, that scarf grows thick and heavy, and the motions upon it slow. When we drift away, it becomes thin and light once more. A black hole, with its enormous mass, thickens this scarf of time most intensely near the event horizon, creating variations no other place in the universe can reproduce. And now, as the thought of time stretches like the very light circling the black hole, the journey invites us to go deeper still. If the edge can make time bend so gently, then inside the dark region, where space-time becomes a one-way flow, every familiar notion will shift even more profoundly. From this slow-moving border, the story will carry us into a place where no return is possible, where time stops being a familiar clock and becomes a single direction. And the journey, still as slow as a resting breath, will continue into that hidden realm. As time at the edge of the black hole begins to flow with unfamiliar rhythms, as the imagined clock slowly drifts away from the universe's usual beat, the journey slips one step deeper into the darkness. From the place where time bends like a ribbon of silk, the mind drifts toward a special boundary, one where every path back disappears without the slightest warning. If time dilation is the gentle invitation to feel the shift, then the next step is the moment of crossing the border the universe sets as an uncompromising rule, the event horizon. It is the moment of no return, yet it arrives quietly. No sound, no line, no signal of light. Just one ordinary second followed by another in which every escape route is suddenly gone. In imagination, the astronaut continues drifting toward that dark ring. There is no door opening, no wall to touch, no sudden change of color. The event horizon is a boundary that exists only in equations and in the fate of whatever passes through it. When the imagined spacecraft slips into this region, every signal sent outward will never escape. But inside the cabin, nothing feels different. Time flows evenly, Light still fills the view, and the moment brings no drama. It is simply the next step in a motion already underway. From the outside, the astronaut will never cross that boundary. His image will slow, dim, and fade into a distant smear of light that never fully disappears. Yet inside his own journey, he moves forward smoothly, passing the invisible threshold in full. This difference creates a soft sense of paradox, like a story told by two people at the same time, each ending true, yet neither able to meet the other. Not a conflict, just the peaceful coexistence of two perspectives flowing along the same path. Once the spacecraft is inside the event horizon, space-time tilts in a way no other place in the universe can mimic. No trajectory allows light to climb back out, and because light is the fastest thing to exist, every other signal is trapped as well. But this does not feel like confinement. It feels like drifting on a river with only one direction. From here on, every path leads deeper into the black hole, a one-way journey drawn by the shape of space-time. In the first moments inside the boundary, the astronaut's body remains safe. Because a supermassive black hole has an enormous event horizon, the difference in gravitational pull between head and feet is too small to create pain or tearing. The idea of spaghettification, the stretching of the body into long, thin strands, still exists, but it becomes fierce only much closer to the center. Here, near the horizon, the stretching is slight, gentle enough to go unfelt. The astronaut isn't twisted or heated. He simply continues drifting along the curvature of space-time, as though entering a long hallway without walls, without ceiling, only silence and the tilt of the universe. The sky around him begins to deform. Stars behind him stretch into pale, red streaks. Blue light becomes red light. Red becomes infrared, then slips into wavelengths no longer visible. As the spacecraft drifts deeper, the light grows weaker, like distant candles pulled long by the wind of time. The sky does not darken all at once. Instead, it becomes a hazy spiral of distortions, where light bends into curves as soft as hair floating underwater. Everything seems to slide away from where it once was, not because of speed, but because space-time itself is shaping the path of light. And soon, that distortion brings the feeling of stepping into a dream without edges. No clear direction remains. No up or down, no left or right. Every direction leads toward the black hole's center, not because of a force pulling, but because space-time's structure has bent so deeply that all paths converge at a single point. If the outside universe is a wide, flat plane, then this place resembles an endlessly sloping surface. Now the astronaut may sense familiar things slipping away, not in sudden disappearance, but like memories dissolving into shadow. The outside world is now distant in both physical space and time. Someone watching from outside would never see him cross the threshold. Any message sent inward would never arrive. But for the astronaut, time flows steadily, unbroken. This is one of the universe's most beautiful paradoxes. Two versions of the same journey, both true, but unable to meet. As the spacecraft continues drifting, a quiet realization comes like a confirmation. From this point on, every path leads deeper into the black hole. Not a warning, just the soft truth of space-time. The flow cannot reverse, yet it carries no panic. It is like recognizing you are sliding down a smooth hill, unable to climb back, but in no rush, simply letting yourself move with the natural slope. And in that moment, with the event horizon now behind and the widening darkness ahead, the story prepares to step into a deeper stage, where the very ideas of space and time begin to dissolve into one another in ways no longer familiar. From here, the journey will move toward the center of the darkness, where classical concepts gently break apart into new thoughts. With the event horizon now drifting behind like a soundless memory, the journey continues into a region where no return is possible. The distortions of light, the stretched red trails of distant stars, all gradually fade into a soft mist surrounding the imagined ship. From the moment that invisible boundary was crossed, space and time begin to blend in unfamiliar ways, as if the universe is rearranging its own rules to guide the astronaut deeper. And once fully settled into this one-way current, a gentle question arises. What truly exists inside a black hole, seen through the lens of general relativity? In Einstein's classical description, inside the event horizon, what we call the distance to the center of the black hole is no longer distance in the usual sense. It is not a place in space to travel toward, but more like a point lying ahead in the astronaut's personal future. This sounds paradoxical, yet in a curved universe, the unbelievable often becomes law. As the ship enters that darkness, it is no longer falling toward a physical location. It is drifting toward its own future, a future in which every possible path leads to the singularity. Imagine time and space trading roles. If outside the black hole one could walk in many directions, choosing many paths, then inside, all directions blend into a single flow. No choice to turn left or right, no option to step backward. No familiar 2 or 3 dimensions, only one direction remains, and it does not lead outward. It leads toward what relativity calls the singularity. But this point is not a place to reach. It is a moment where all events converge, a moment written into the fabric of space-time itself. In this gentle telling, the singularity is not something frightening. It is simply where our current laws no longer apply. It is like the edge of an old map where people once wrote, "Beyond this point, nothing is known." Not because the place is terrifying, but because our knowledge is still too coarse to describe the deep structure inside space-time's well. In classical physics, it is where density approaches infinity, where curvature becomes unbounded. But in this sleepy story, the singularity appears instead as a symbol of our incomplete understanding, a quiet reminder that the universe holds shapes we have not yet imagined. As the astronaut continues falling, the sensation of drifting through space gives way to something subtler, drifting through time. Not accelerating, not tumbling, but moving down a river without banks or bottom, only depth. The ship does not plunge or tremble. It simply follows the natural flow carved by space-time. Inside this darkness, distance is no longer something to measure, and time no longer ticks in small familiar beats. Everything blends like faint ripples across a lake at night. If we imagine further, we might picture the astronaut moving through layers of space-time that curve downward more strongly with each passing moment. These curves do not pull, they guide, like a soft breeze nudging a boat farther out. No fixed direction remains, only the feeling of heading towards something no one has ever precisely described. The path ahead is not a rigid shape, but shifts with the way space-time contracts. To fall here is no longer to move through space, but to advance through time, time in which every point leads toward the same future. General relativity, in its classical form, describes this journey as unavoidable. Once inside the event horizon, even standing still cannot change the outcome. Even light, the fastest thing the universe has ever known, cannot pause its descent. This is not a lack of freedom. It is simply how space-time bends itself into a single corridor, like dust carried by a river as it approaches a waterfall. The certainty of this journey does not bring weight. It brings a gentle surrender, as though the universe is softly guiding you toward a place where every path meets. Here, light appears less and less, not because darkness devours it, but because light can no longer hold its own path against space-time's bending. Stars behind stretch into long streaks before finally dissolving. Shapes soften, colors fade. The familiar world blurs like a painting swallowed by fog. And in this moment, as the astronaut moves deeper into a region that classical physics can describe only in the vaguest language, the story opens yet another horizon. For general relativity is only one piece of the picture. Beyond it, quantum mechanics waits to add its voice. But before stepping into the realm where the two worlds overlap, this one-way journey continues, soft as breath, gliding toward a place where time no longer carries its old meaning, and new questions prepare to take root. As the one-way journey inside the black hole sinks deeper into the curved layers of space-time, as the singularity appears like an unavoidable point in the astronaut's future, the story needs a gentle shift, one that brings the mind back outside, where another phenomenon is quietly unfolding at the black hole's edge. Because while the region inside the event horizon is ruled entirely by general relativity, the world outside becomes a stage where quantum mechanics begins whispering its own secrets. And to see the full picture, the journey must momentarily pull back, viewing the black hole from the outside, not through the bent starlight, but through a very special light emerging from the event horizon itself. A faint, strange light that comes not from accretion or collisions, but from the trembling of the vacuum. In the quantum view, the vacuum is not empty at all. It is like a tiny ocean of microscopic fluctuations, where particles and antiparticles appear and vanish like delicate ripples. These pairs always arise together and quickly annihilate, leaving no trace. Normally, they vanish too quickly to form any observable event. But when this happens near the event horizon, something unusual can occur. If a pair forms right at the black hole's edge, sometimes one particle falls inward while the other escapes outward before it can be cancelled. When that happens, a distant observer sees something remarkable. It appears as though the black hole is emitting light. Not bright light, but rays so faint they are almost impossible to detect, visible only through delicate mathematics. This is Hawking radiation, one of the most beautiful discoveries of 20th century physics. It is not light in the usual sense, but the soft imprint of quantum mechanics meeting strong curvature in space-time. In a sleepy metaphor, each Hawking particle feels like a tiny whisper sent by the black hole into the universe. Not loud, not urgent, just a subtle echo from the quantum world. Each escaping particle is a small piece of energy the black hole gives back to the space around it. And this process unfolds incredibly slowly. For a supermassive black hole, the radiation is so weak that it would take longer than the age of the universe to lose even a tiny fraction of its mass. But the importance lies not in speed, but in principle. A black hole is not completely silent. It has its own temperature, its own way of exchanging energy, its own gradual life cycle. Rules even the darkness must obey. A black hole's temperature is inversely proportional to its mass. The larger it is, the colder it becomes. A supermassive black hole at a galactic center has a temperature nearly equal to absolute zero, so cold that if it glowed, its glow would be fainter than the breath of a dust mote. Yet even then, a few Hawking particles may drift outward, like microscopic droplets evaporating from a quantum lake. From a sleepy imagination's perspective, this becomes the black hole's quiet, breathing breaths the universe must use mathematics to detect. Intriguingly, this radiation causes the black hole to lose mass over time. Though incredibly slow for the large ones, it is still a life cycle. A smaller black hole evaporates faster, and in its final seconds, the radiation becomes so intense it could produce a burst of tremendous energy. But the large ones, those dark mountains of the cosmos, fade away only over timescales far longer than the lifespans of galaxies. Their ending is not dramatic, but a soft dissolution, like cold smoke thinning into space. Far outside the black hole the astronaut crossed, hawking radiation continues. It does not affect the inner journey or alter the one-way flow described by general relativity. But it opens another view. A black hole is not merely a gravitational trap. It is also a quantum object, capable of emitting energy and possessing a lifespan. The meeting of these two worlds, general relativity and quantum mechanics, creates a picture both contradictory and astonishingly beautiful. The tiny particles escaping from the event horizon are like notes the black hole sends into the universe. Not messages about the inside, but reminders that the black hole itself obeys quantum rules. This is the foundation of the information paradox, the great question of whether information falling into a black hole is lost forever. But that story belongs to another chapter in the flow. For now, it is enough to feel that even in absolute darkness, there are still faint quantum whispers, signals fragile but persistent, showing that the universe is never fully silent. And as that delicate light dissolves back into the night of space, the story prepares to open the next doorway, where deeper secrets of information and darkness begin to intertwine. As the faint glow of hawking radiation slowly fades into the night of space, as tiny particles slip away from the edge of a black hole like delicate whispers the darkness leaves behind for the universe, the story gently guides us into another field of thought. If each escaping particle is a small loss for the black hole, and if over vast stretches of time a black hole could evaporate entirely, then a question begins to form, softly, like a drifting mist. What happens to all the information that once fell inside? It isn't a hurried question, nor one heavy with debate. It arrives like a quiet thought hovering right before sleep takes over. A question that has made generations of scientists pause and wonder, yet here it is told with the unhurried rhythm of a peaceful night. Quantum mechanics, with its own unwavering rules, insists that information can never be destroyed. Not information in the everyday sense, but the microscopic details describing the state of matter and energy. In the quantum world, even if an object burns, decays, or changes shape entirely, the information about its original state must remain somewhere within the products of that process. This principle is fundamental, like a thin, essential thread woven through the fabric of quantum theory itself. But when something falls into a black hole, that principle seems to face its greatest challenge. When anything falls into a black hole, from starlight to cosmic dust, from a massive star to the smallest of particles, it crosses the event horizon and disappears from the universe's ability to observe. If the black hole simply kept all that information inside, perhaps there would be no issue. But once Hawking radiation enters the picture, a problem appears immediately. Hawking radiation carries no pattern, no imprint, no structure from within the black hole. It's merely the product of quantum fluctuations near the event horizon, a process that seems random, carrying no hint of the things that fell inside. If a black hole eventually evaporates completely, all the information within appears to dissolve into nothingness. This gently places two great pillars of physics, general relativity and quantum mechanics, into quiet disagreement, like two instruments playing melodies that no longer match. General relativity accepts the disappearance of information because inside the event horizon, there simply is no way out. But quantum mechanics says such a thing is impossible. And so the question appears slowly, like the light of a distant star. Where does the information go? To imagine this puzzle more clearly, people often speak of the no-hair theorem. In familiar imagery, a black hole seen from the outside can be thought of as a personality-less object. It doesn't matter what falls into it, a star, a cloud of gas, or even a fanciful spaceship. From the outside, the black hole can only be described by a few simple numbers: its mass, its spin, and its electric charge if it has one. Everything else, the shape of the falling object, the way it rotated, its internal structure, its composition, vanishes from the picture. The black hole keeps no fingerprints of the things that touched it. It is smooth, simple, like a dark stone polished until no identifying marks remain. That smoothness deepens the mystery. If its interior is full of information, yet its exterior reveals only 3 basic parameters, does that mean most information is erased? Or is it hidden somewhere behind the event horizon? Or perhaps Hawking radiation, random as it seems, actually carries tiny encoded traces we aren't yet sensitive enough to detect. Many possibilities have been proposed, but none has become the final answer. Each hypothesis is like a small story told around the lamp of imagination, glowing briefly before fading in the ongoing discussions of scientists. But in the gentle atmosphere of this tale, we do not dive into argument. We simply feel that the black hole, in its silence, carries one of the universe's greatest secrets about information. A secret the cosmos has not yet decided to reveal. So the question, where does the information go, becomes more than a scientific puzzle. It becomes a soft melody leading us toward the sense that some things, no matter how long we look or how deeply we think, remain beautifully unclear. And it is that very obscurity that makes the universe feel larger. Looking at the whole picture again, the information paradox appears like a dim light hovering at the edge of darkness. It causes no panic, no tension, only the presence of an ancient secret placed gently in the middle of a quiet night. Each time we think about it, the secret does not unravel. It simply becomes softer, deeper. When we close our eyes, we might imagine the black hole not as a place that destroys information, but as a place that hides it within structures we have not yet reached. And while that secret still rests there, the story is ready to lead us toward another idea. One suggesting that perhaps information is never lost at all, but instead recorded on the very boundary of the black hole, like a 3-dimensional image encoded onto a thin surface. But that belongs to the next chapter, where the holographic principle begins to whisper its own quiet message, as the question of information still drifts in the darkness, like a tiny spark swaying gently in endless space. The journey becomes ready to welcome another idea, one known as one of the boldest possibilities ever woven to reconcile the tension between quantum theory and black holes. If the information paradox is like a closed door, leaving us uncertain whether information is shredded or simply hidden, then the hologram principle appears like a key placed softly beside that door, not claiming to unlock it, but suggesting that there may be another way through. And to sense that pathway, we need only imagine the universe through an entirely new lens. The idea begins with a simple picture. Imagine holding a thin, 2-dimensional film in your hand. Its surface is flat and delicate. On it are patterns so fine the eye can barely detect them. But when you shine light on it at just the right angle, those faint patterns rise into a three-dimensional image, lifting off the surface as if a real object were appearing before you. This is a hologram, a three-dimensional shape encoded entirely by information on a two-dimensional sheet. The real, three-dimensional world of an object is compressed into a thin layer, and when light interacts with it, that compressed information blossoms back into space. The holographic principle in theoretical physics works in much the same way, but at a scale so vast that imagination must stretch across many layers to hold it. According to this principle, all the information contained within a three-dimensional region of space can be completely recorded on the surface surrounding that region. There is no need to look inside. The structure of the boundary alone may contain enough to reconstruct the entire interior. This is not a metaphor, but a possibility mathematics and quantum gravity have hinted at again and again. And if we apply this idea to black holes, the event horizon, the surface enclosing that absolute darkness, could hold all the information about whatever has fallen inside. Instead of being torn apart or erased, that information would be encoded on the boundary of the black hole itself. In a gentle imagining, we might picture the event horizon as a thin, invisible membrane, where each falling particle leaves behind a slight ripple, a symbolic mark we cannot read, but the universe can. Gathered with enough sensitivity, those ripples could contain the full story of the object that crossed the horizon. This is one of the ways physicists try to preserve the principle that information is never lost. If a black hole evaporates through Hawking radiation, and if that radiation can carry information encoded on the event horizon, then perhaps the information does not vanish. It simply changes form. It shifts from the story of matter falling inward to delicate vibrations along the boundary of the black hole, and finally becomes subtle structure in the radiation escaping outward. This cannot be proven through current observations, but it opens a pathway where the quantum world and gravity no longer collide. In the lullaby-like language of this story, the hologram principle whispers that every memory, every vibration, every tiny motion may be recorded somewhere, even when we cannot see it. If the imaginary astronaut in our tale were to fall into a black hole, perhaps his entire story, the rhythm of his heartbeat, the fleeting thoughts passing through his mind, the light glancing across the cabin walls, would be written onto the invisible surface of the event horizon. Not in the familiar way we understand information, but as deeply encoded patterns woven into the fine mesh of space-time. One of the clearest settings in which the hologram principle reveals itself is in the idea known as ADS-CFT, a famous mathematical correspondence in theoretical physics. Without needing to explore its details, it is enough to know that it shows how a universe with gravity in three-dimensional space can be described entirely by a quantum theory without gravity on the two-dimensional boundary surrounding it. From this equivalence, we learn that a boundary may hold the full information of the interior. And if that is true in simple models, perhaps it is also true, in some profound way, for real black holes in the universe. This idea makes the picture of a black hole feel lighter and stranger. Instead of a dark abyss swallowing everything, it becomes a surface rich with symbols, like a scroll filled with markings too fine for the eye to read. From afar, it remains a perfect, featureless shadow. But in its microscopic structure, it may be a place that carries stories we once believed were lost. This does not make the black hole any less mysterious. It simply transforms the mystery into something more abstract, more delicate, something as soft as breath touching a cold mirror. If we view the entire universe through the light of the hologram principle, we might imagine that the three-dimensional space we live in is really an image rising out of information encoded on the farthest boundary of the cosmos. As though everything we see, every action, every sliver of memory were written on a surface so distant we could never reach it. This idea is not meant to deny reality, but to remind us that reality may be more intricate and beautiful than we directly perceive. And in this moment, as the hologram principle unfurls like a thin silk veil draped over the darkness, the story returns to the astronaut drifting inside the black hole. Perhaps instead of disappearing, his story simply changes shape, becoming those faint ripples on the boundary his vessel once crossed. No one can read those ripples, but that does not make them any less real. As this thought settles like stardust, the journey becomes ready to move toward other hypotheses, where even bolder ideas, like the firewall or the fuzzball, wait to be told in the slow, steady breath of the universe. As the idea of the hologram principle still drifts softly through the mind, like a thin veil laid over the surface of darkness, the journey opens yet another branch, one where bolder, stranger, and almost myth-like scientific hypotheses begin to appear. If the hologram principle hints that information might be encoded on the event horizon, then these next ideas are like different versions of the same lingering question. What truly lies at the boundary between the known and the unknown? None of these hypotheses are confirmed, but each carries its own distinct beauty, like stories whispered around a small fire in the deep night of the cosmos. The first hypothesis arrives with a simple name, yet one that evokes a fierce image: the firewall. According to the classical picture from general relativity, an astronaut falling into a supermassive black hole would feel nothing unusual upon crossing the event horizon. No wall, no flash of light, no sudden jolt signaling the point of no return. But as physicists tried to reconcile the information paradox, several quantum arguments began to suggest that perhaps this boundary is not so quiet. Perhaps, right at the event horizon, there exists a ferocious wall of energy, a firewall. If this is true, anyone touching that boundary would be burned instantly, with no chance of moving further in. Not because of hot matter, but because quantum fluctuations form a dense region of energy preventing information from slipping into total darkness. Though the idea seems like a sharp cut across the gentle picture of a black hole, it remains a possibility, because it protects the principle that information cannot be destroyed. The firewall becomes like a colossal watchtower standing at the boundary, enforcing a rule that contradicts everything general relativity once promised. Yet despite its intense and dramatic nature, the hypothesis is not a declaration. It is only a suggestion. In the soothing atmosphere of this story, the firewall is not something frightening, but a strange silhouette appearing when we shine light into the region where two great theories collide. The second hypothesis, softer in imagery but no less daring, comes from the world of string theory, the fuzzball. Instead of imagining a black hole as a hollow interior leading to a singularity, fuzzball theory suggests that the entire volume of the black hole is filled with complex quantum structures. No more infinite point at the center. No more smooth, empty interior. Instead, the black hole becomes a tangled mass of quantum strands, woven into a dense network, soft yet resilient in its own peculiar way. The name fuzzball reflects this picture. No 2 points alike, no smoothness anywhere, only a cloud of quantum energy and information. If the fuzzball idea is correct, the astronaut cannot sink into the black hole as classical pictures suggest. He would encounter this quantum structure long before reaching any singularity. Not a violent firewall, but not a calm, empty void either. More like a forest of intertwined quantum threads, where every tiny vibration stores information about what has fallen in. Fuzzball theory resolves the information paradox by saying that there is no inside where information could be swallowed. Everything rests within this expanded quantum structure at the surface. Between the firewall and the fuzzball, there exists another group of gentler, more delicate ideas known as soft hair. This is the notion that beyond the three basic parameters permitted by classical theory, mass, spin, and charge, a black hole may have additional tiny features, incredibly light and subtle, capable of storing information. These features are called soft hair, not in the physical sense, but as faint informational markings clinging to the event horizon. If they exist, they might serve as codes, preserving traces of the objects that once fell inward. The information does not vanish. It is written into this layer of soft hair in ways we do not yet understand. Soft hair paints a gentler picture than either firewall or fuzzball. No scorching wall, no thick quantum tangle, only tiny variations, subtle vibrations on the event horizon, where each falling event might leave behind a faint but persistent mark. When these three ideas, firewall, fuzzball, and soft hair, are placed side by side, we do not see conflict, but instead a garden of scientific imagination. Each hypothesis is a different path, each path a unique attempt to understand the great question of information and black holes. None of them has been proven true, but their existence shows that physicists are trying to observe darkness from many angles. There is no final answer, only temporary viewpoints that serve as invitations to reflect. In the gentle stillness of this journey, the firewall, the fuzzball, and the soft hair do not appear to confuse the listener, but to reveal that science itself can sometimes feel like poetry. It does not hold only precise equations. It holds abstract stories, evocative images, and the human effort to understand the darkest places in the universe. And as these hypotheses blend together like strokes of ink in a cosmic watercolor, the story carries us forward into another chapter, where the astronaut continues his journey, traveling toward the very end of darkness, where layers of mystery rise and fall like waves brushing the shore in a long night. As the ideas of the firewall, the fuzzball, and soft hair still drift through the realm of imagination, like different branches of a scientific legend that has yet to find its ending. The story slowly drifts toward another landscape of thought, deeper, quieter, more dreamlike. If those models are like paintings capturing the structure of a black hole from different angles, then there is another aspect that makes black holes so unique that modern physics must pause and reflect: entropy. A concept that seems simple, yet when it touches a black hole, becomes a key that unlocks questions about the arrow of time, the nature of information, and mysteries far beyond any single object in the universe. Entropy, in the gentlest sense, is a measure of disorder, the number of ways a system can be arranged on a microscopic level. Not disorder in the everyday sense, but the diversity of possible configurations of particles, even when the system looks simple from afar. A warm glass of water has higher entropy than a cold one, because its molecules have more ways to move. A book neatly placed on a table has lower entropy than the same book scattered by the wind. But entropy is more than the loss of order. It is the direction in which time seems to flow. The universe began in a remarkably ordered state, and with every passing second, entropy slowly increases, as if time is a river flowing from quiet valleys toward wide open plains, where disorder becomes natural. When physicists looked at black holes, they were startled to discover that these dark, solitary objects possess enormous entropy. And even more astonishing, the entropy of a black hole does not scale with its volume, as with ordinary physical systems, but with the area of its event horizon. Bekenstein and Hawking found that the entropy of a black hole is determined by the area of the boundary that surrounds it. This is like measuring the information content of a room not by its interior volume, but by the surface area of its walls. That strange idea became the foundation for the hologram principle the story just passed through. But long before it shaped our understanding of a three-dimensional universe encoded on a two-dimensional boundary, it first appeared as a peculiar puzzle of thermodynamics. If entropy measures disorder, then black holes are immense reservoirs of entropy in the universe. Every time matter falls into a black hole, its entropy does not vanish. It adds to the area of the event horizon. When a star, a cloud of gas, or even a tiny particle drifts into the darkness, the black hole's boundary expands ever so slightly. A tiny increase, but still a step upward in entropy. Even though information inside the event horizon seems to disappear from the observable world, the entropy of the black hole keeps rising in a beautifully consistent way. And this is where the arrow of time appears. In physics, no fundamental equation requires time to move from past to future. The equations work, the same even if you run them backward. But entropy does not. Entropy only increases or stays the same. No one has ever seen entropy spontaneously decrease in a large system. So when the entropy of a black hole rises, it becomes evidence that time in the universe has a direction, and that direction always points towards states that are more chaotic, more varied, more uncertain. A black hole, then, is not merely an object of immense gravity. It is a place where time speaks most clearly. Time does not speak in words we can hear, but in how it shapes the destiny of entropy. When something falls into a black hole, it does not just cross a physical boundary. It steps into the flow of time in a way that cannot be reversed. The entropy of the black hole afterward is higher than before, and that alone makes past and future fundamentally different. As physicists studied this picture, they were forced to rethink the relationships between time, information, and space. In flat space, entropy spreads. In curved space, entropy shifts along dimensions we can barely imagine. And inside black holes, entropy condenses onto the boundary, as if space itself were trying to reveal that its deepest structure lies not in volume, but in area. If we return to our imaginary astronaut, drifting deeper into the darkness, we might see his journey as the path of information becoming entropy. Not in the sense of dissolving, but in the sense of joining a larger picture, where time is the final guide for every event. Each moment he travels changes not just his location in space-time, but the entropy structure of the universe, even if only by a tiny amount. And as this thought settles, we realize that black holes, these seemingly simple regions of darkness, force humanity to confront its most profound questions. What is time? Why does it have a direction? How can a surface hold all the information of a volume? And is entropy the background music the universe uses to guide every motion? In the stillness of this story, those questions do not need final answers. They only need to echo softly, like the gentle resonance of a long night, preparing to guide us into the next chapter, where doors to other universes, quantum bridges, and the strangest hypotheses await their moment to unfold. As the thought of entropy still drifts like a thin mist across the layers of space-time, as the idea of the arrow of time makes the universe feel like a one-way flow from order into disorder, the story opens a new space, a space for bolder, more dream-soaked imaginings. For if a black hole is a place where time narrows toward a single future point, then what lies beyond that point? And if the boundary of a black hole can store information in ways so delicate we barely understand them, could the space inside connect to somewhere else? These questions open the realm of hypotheses such as wormholes, white holes, baby universes, and the multiverse. Ideas that are scientific, yet tinged with the breath of distant dreams. One of the earliest visions of a doorway linking two regions of space emerged in the early 20th century, the Einstein-Rosen bridge. According to general relativity, certain solutions to the field equations allow for a tunnel connecting two distant points in space. These are called Einstein-Rosen bridges, or wormholes. In imagination, they resemble short passageways piercing through the fabric of space-time. Traveling across ordinary space might take millions of light-years, but passing through a wormhole could take only a moment. However, in classical models, these bridges are unstable. They collapse so quickly that no object could pass through. Not even light can cross from one end to the other in time. Wormholes, therefore, exist as beautiful but fragile mathematical solutions, like soap bubbles that form and vanish the moment you touch them. They cannot become stargates as in science fiction, at least not according to classical descriptions. But that has never stopped human imagination from stretching further. In the culture of science fiction, wormholes are seen as gateways between galaxies, shortcuts through vast space, luminous passages that carry travelers to worlds otherwise unreachable. Even if reality may never permit such journeys, these images add a gentle, dreamlike layer to our path, like a soft blue tint washing across the scientific story. Alongside wormholes, another idea also arises from Einstein's equations: the white hole. If a black hole is a place from which nothing can escape, then a white hole is a place into which nothing can enter. It is a kind of mirror image. Instead of swallowing light, it pushes light outward. If the two objects were connected, one could imagine matter falling into a black hole and emerging from a white hole somewhere else. This creates a channel through space-time. Matter vanishes here, reappears there. Though no white hole has ever been observed, the idea remains as a suggestion of a symmetry the universe might possess. It does not claim that white holes truly exist, but it allows us to imagine that darkness may not be an ending, but a passage to another side of space-time. One of the most beautiful ideas in this family of thought is the baby universe. Certain theoretical models. Within a black hole, space-time may continue unfolding in ways invisible from the outside. Instead of collapsing into a singularity as classical descriptions predict, space may curve into a new direction, expand, and become a separate universe, detached from the parent universe. If this is true, every black hole might be a doorway to the birth of a new cosmos. The laws within that cosmos might resemble or differ from our own. The expansion inside a baby universe might echo the early moments of the Big Bang, and we, creatures of the parent universe, could never look inside to see this happening, just as those in a baby universe could never look outward to know they were born from a black hole. This idea opens a new way to imagine the multiverse. We need not picture an infinite sea of parallel universes existing independently. Instead, each black hole may be the seed of a new universe. Like a Bodhi seed falling to the ground and sprouting into a new tree, a black hole could carry the full potential for the birth of an entire cosmos. In this picture, the universe is not singular, but a lineage of spaces, each born from the darkness of the one before it. All these ideas, wormholes, white holes, baby universes, and the multiverse, are hypotheses. They have not been proven, not been observed, and may never become reality. But in this bedtime story of the cosmos, they do not need absolute certainty. They need only be gentle suggestions, faint glimmers leading toward the places human imagination has always longed to explore. A black hole, once seen as a place of endings, becomes instead a shimmering hint of infinite possibilities. And while the astronaut continues falling deeper into the dark, carried along the one-way flow of space-time, these ideas form a separate sky, one filled with untestable possibilities that nonetheless bring a strange, calming quiet. They do not demand belief. They simply invite the listener to rest their mind in a dream space where any story might open like a parallel path. As that layer of dreaminess settles and then fades, the journey prepares to return once more to the astronaut, where endings and beginnings meet again in the dark. As the ideas of wormholes, white holes, baby universes, and the multiverse still drift in the imagination, like clusters of soft, glowing mist. As the possibility that a black hole might lead somewhere else lingers like a hazy echo in the mind, the journey returns to where it first began, to the astronaut still falling deeper into the dark. The hypotheses about pathways between universes, about secret corridors of space-time, beautiful as they are, remain only branches of thought. But he, the one who crossed the event horizon long ago, continues along the one-way flow shaped by general relativity. And now, as the fabric of space-time around him grows ever more curved, the story returns to his perspective, where every outside theory becomes nothing more than a distant whisper. At this moment, the astronaut is very close to the region classical descriptions call the singularity, not a physical point to touch, but a moment in the future toward which all paths converge. No direction remains, no velocity to measure, no light to reveal the surroundings. Everything around him becomes soft, distorted, stretched, as though space-time itself is reshaping with each beat of a silent song. The deeper he falls, the farther his time drifts from the time of the universe outside. The deeper he falls, the more light slips beyond his ability to sense. Yet the motion continues, gentle, like a stream carrying a leaf toward the final bend of a river. From here, the story can be told in two versions, both existing side by side, like two faces of the same dream. In the first version, the version belonging to classical general relativity, the astronaut continues falling exactly as the equations predict. Space contracts, time stretches, and the flow leads straight to the singularity. There is no panic, no tearing apart, only a silk-soft acceptance. What remains is a convergence, every motion, every memory, every vibration drawn toward that final point. This version feels like a slow fade-out, the last light dissolving until only complete surrender remains. An ending not of loss, but of returning to the original stillness of space-time, as though he is dissolving into the primordial nature of the universe, where matter and time are no longer separate. In the second version, imagination opens another path, one suggested by many hypotheses, but proven by none. In this version, as the astronaut reaches the region where general relativity can no longer describe reality, space-time curves into a new direction. Instead of converging into a singularity, space opens, expands, becoming a doorway into another dimension. A baby universe may be forming, or a strange new region of space may be waiting. Not a blaze of light, not a triumphant escape, just the quiet sense that a new structure of space-time is unfolding. If this version is true, The astronaut might cross into a threshold we cannot observe. But the story does not follow him. The camera stops at the edge, holding the mystery in place. We do not know where he goes. We do not know the shape of the space beyond. We do not know what laws of physics wait for him there. Everything fades like mist drifting into the night. This idea is not meant to offer hope or certainty, only to preserve the feeling that the universe still contains regions untouched by knowledge. No matter which version one chooses, the emotion at the end of this journey is not fear. It is acceptance. Questions softening, tensions loosening. Like someone gazing at the night sky and realizing they do not need to understand everything in order to feel at peace. The astronaut no longer struggles against his fate. He simply moves with the flow space-time has drawn. No longer resisting, no longer searching for a way back. Only a gentle curiosity about whatever lies ahead, even knowing the answer may never arrive. His journey, from leaving Earth to approaching the black hole, to crossing the event horizon, passing through layers of curved time and space, and now facing an open ending, becomes a story of graceful release. Not the release of dreams or hope, but the release of the need to know everything. In the heart of a black hole, where no light escapes, it is acceptance of mystery that makes the final step beautiful. In the last moment where the story pauses, we do not see him dissolve, nor watch him step into a new world. We only see the darkness soften, like a velvet curtain lowering gently. Both versions intertwine like two branches of the same dream, neither canceling the other, both allowed to exist, leaving behind the resonance of an open ending, where no period is needed, only a quiet widening of the unknown. And as that layer of darkness settles over the entire scene, the story prepares to enter its final part, the part meant for the listener, where the astronaut's journey ends in silence and they return to their own night sky. As the darkness in the astronaut's final moments closes lightly like a velvet curtain draped across the universe, as the open-ended branches of his story still linger like thin threads that have not yet touched the ground, the tale slowly returns to where every imagined journey begins. The quiet room where the listener lies, the soft light in the space breathing as slowly as the night itself. From the world of curved space-time, from the bending of light and the depths of physics, the story gently retreats, layer by layer, so the mind can return to a small, still, human kind of quiet. And in that stillness, everything the listener has just traveled through begins to drift back like a soft stream. A stream not meant to explain, not meant to test knowledge, but simply to place the images that passed by into a gentle corner of the listener's thoughts, a place where imagination and sleep can rest beside each other. We began our journey with the earliest ideas of black holes, in a quiet night where the question, "What is inside a black hole?" floated into the air like a thin ribbon of silk. We saw how humanity first touched the idea of black holes through history, from the dark stars of the 18th century to the equations of Einstein and Schwarzschild, and then to the moment John Wheeler named that region of darkness with two haunting words: black hole. We followed the deaths of massive stars, leaving behind pockets of space-time where gravity grew strong enough to keep even light from ever returning. As the spacecraft drifted toward the black hole, its structure unfolded like a scientific poem. The event horizon as a line of no return, the photon sphere as a shining loop where light is forced to orbit, the accretion disk swirling like a glowing halo of heat around the darkness. We looked upon the family of black holes, stellar mass black holes, supermassive ones at the hearts of galaxies, the elusive intermediates, and the hypothetical primordial ones born at the dawn of time. When the astronaut approached the event horizon, time changed its rhythm. For him, everything flowed naturally, like a small stream. But for the universe outside, millions of years could have passed. At that boundary, space and time trade roles, and falling into a black hole becomes a journey into one's own distant future. He crossed that line with no alarm, no flash of warning, just a moment passing, and every path back simply disappearing. The story continued with the classical description of the black hole interior, where the singularity is not a place, but an inevitable moment. Then quantum mechanics entered the scene, with pairs of particles and antiparticles appearing at the horizon, giving rise to Hawking radiation, the faint breath of a black hole across billions upon billions of years. The information paradox opened like another doorway, leading us to wonder whether information truly gets shredded inside a black hole or merely hidden away. Then the hologram principle touched the story like a line of invisible text written on the surface of the event horizon. Models like the Firewall, Fuzzball, and Soft Hair drifted by like leaves falling onto a lake, each one a way humanity tries to understand what darkness refuses to reveal completely. Then Entropy and the Arrow of Time brought forth another layer of reflection. The black hole became a reservoir for the universe's disorder, proof that time does not sit still but always flows toward higher entropy. In the presence of a black hole, time is no longer background music. It becomes the conductor, sending every event toward its end. And finally, the bold ideas of wormholes, white holes, baby universes, and the multiverse appeared like dreams physics saves for its darkest corners. Not to claim they truly exist, but to remind us that even when facing absolute darkness, the human mind finds ways to open new doors. Now, as the astronaut has fallen to the point where the story can no longer follow, as his journey closes in a darkness as light as mist, the tale returns to the listener. In the familiar room, a faint light rests somewhere in a corner, and the listener's eyes may have already grown heavy. The journey just taken does not require alertness, only release. If anything remains, it is the feeling that the universe is so vast that every question becomes just a small note in an endless symphony. We have traveled from history to structure, from time to quantum theory, from entropy to the thresholds of other universes. And after all of that, the most honest thing we can say is this: we do not know for certain what lies inside a black hole. But that very unknowing is what makes the universe beautiful. If everything were clear, nothing would remain to feed the imagination. The astronaut in this story is only a tiny image, just as each of us is. We look up at the night sky, see the faint lights of stars billions of years away, and recognize that we are only a small point in a much larger picture. But that smallness is what allows us to feel the universe's beauty as something gentle, something not meant to frighten, but to quiet the heart. And so the story ends, not with a period, but with an invitation to close your eyes and let the universe's questions drift in your subconscious like quiet points of light. An invitation to let your mind float in the space between waking and sleep, where everything you've heard melts into soft imagery. And in that space, sleep arrives like a natural tide. Tonight, as every sound grows softer, let the universe lull you to sleep with its vastness.